Okay, so thank you, Miguel, and thank you for the organizers to give me the opportunity to present, I guess more science results about MAGIC and LST, who are my favorite ACTs in this case. So I guess I can use this. Okay. So yeah, I will focus on transient sources with MAGIC and LST1, and so I guess we had already some introduction in the previous session, and also a nice introduction by Alim on the technical side, so how we receive these alerts and how we react to them. And the advantage of using a cherry telescope is that they are really sensitive to short duration events. So, I mean, we can probe transient events in a really nice manner because we have this large collection area. And in particular, MAGIC and LST specialize in fast follow-up, so within a few tens of seconds from the event and the observation at low energies. So small introduction about MAGIC and LST1. So they are both in La Palma, which is one of the Canary Islands in this Observatorio Roca de los Muchachos. And for MAGIC, so we have two telescopes. Actually, we had just one until 2009, and then since then we have two telescopes. And then LST1 actually is the first large-sized telescope prototype of the Cherokee telescope array. And it is the first LST, which is now in La Palma there. And there will be other 3 LSTs. Actually, construction of the second one will start soon, possibly next month, and all the others will follow, the other 2. And also we will have also some medium-sized telescopes. So there will be 9 of them in this so-called alpha configuration, but these will be built a bit later. And also the fact that we have LST1 close to the 2 MAGICs allows us to actually do joint observation between them. And so actually we can have 3 telescopes observing at the same time, and so we can increase the sensitivity. And a bit more in detail about MAGIC. So, as I said, 2 telescopes. We observe from around 50 GeV, but actually with a different kind of trigger, we can go down to 30 GeV. For example, when we observe pulsars. The field of view, as any ACT, is not so big. In this case, is 3.5 degrees. So we need to point where we want to observe. So we know where our source is, and we point there. And yeah, for an ACT, is quite light. So 70 tons. It seems like quite heavy, but actually it's quite lightweight for a Cherokee telescope. And this is because we want, for example, to slew fast towards, for example, when we receive GRB alerts, we want to slew to them in a fast way. In this case, we have 7 degrees per second. So if you see the MAGIC telescope was doing with this speed, it's quite impressive. So they are 70 meters, so they are quite big. So it's quite impressive. And one particular thing for transient observations, since the duty cycle of ACTs is limited, actually with MAGIC we can have some hardware conditions with which we can observe, for example, during a moon, or well, not full moon, but when we have, for example, a moon half phase or so on, and also at high zenith angles. So this gives us more observation time to observe transients. Instead, LST, as I said, now it's in La Palma, but actually it was inaugurated in 2018, and since then it's in commissioning phase. And this commissioning phase is going on despite the pandemic, a volcanic eruption that we had last year, then supply chain crisis. So we are going, we have many situations that are making the commissioning more difficult, but we are going through it. And since January 2020, we took around 800 hours of data. And actually, we are close to release our performance paper, where we show indeed the performance of LST, which is in this case, for example, as shown here, is compared to the MAGIC one. Of course, LST is a single telescope, so the sensitivity of a single Cherokee telescope is not as good as a stereoscopic one, where we have 2 in MAGIC. So, I mean, this is what we expect for a monotelescope. So, I mean, the sensitivity is what we expect. And the thing of LST is that we, thanks to it's bigger reflector, we can go down to lower energies. In this case, as I said, MAGIC is around 50 GeV, but with LST we can go down to 20 GeVs. And the field of view is a bit bigger and it's a bit heavier, but in any case, it was designed in order to point to any point in the sky within 20 seconds. So it will be even faster than MAGIC. And here I also show the spectrum of the Crab Nebula, so the standard candle of very energy astrophysics, just to show that LST can reconstruct, in this case, the spectrum down to around 25 GeV. So basically, we are very close to the energy threshold for which LST was designed. I will not spend too much time on this because basically this is just a scheme of the automatic system of MAGIC. I will show also the one of LST, but since Halim already showed it, I can just go through quickly. But basically it's, I would say, quite similar to the one of S in some parts. And of course, we have automatic reaction to some kind of alerts, specifically GRBs and neutrino alerts coming from IceCube. And yeah, it will be soon updated to this new GCN Kafka system and also to handle gravitational waves. And here again, the one from the LST, it's also, I mean, similar. Here we have also the connection to the real-time analysis so that we can also send scientific alerts if we see some, I don't know, maybe some hotspot during one of the observations that we do. So we can send alerts to the outside community. And then actually this will be at some point replaced by a transient handler, which is common to the CTA northern site. So for the moment, it is specific to the telescope, but at some point it will be replaced by one that will control, let's say, the array. And yeah, coming to more science results. So I will start with GRBs, which are, let's say, the prototype of transient sources. And as we have seen before, I mean, observing GRBs can be quite challenging with the Cherenkov telescope. So we have the field of view that is not so big, so we need to rely on external facilities, Swift, Fermi, and so on, to get the alerts. And of course, this introduces some delay on the observation. So, for example, because of this, we may miss, for example, the prompt emission, which is one of the more interesting phases of GRBs. Then they are distant, so we have absorption of the very high energy gamma reflux due to the extractive background light, and then the duty cycle is limited because, yeah, as we have seen, we can only operate during night with the moon or good weather and so on. And also, sometimes the localization is quite large and rough. So in this case, we need to do some kind of tiling in order to cover the error region that is provided. Coming to some scientific results regarding MAGIC. So in 2019, in January, we had the detection of this GRB 190114C, which was quite bright and also at a moderate distance, at least as far as GRBs are concerned. And so if you see also here from the light curve, you see here the time on the x-axis. So basically we have the first off point of MAGIC, which is basically 1 minute after the initial alert that we received, in this case from Swift. And what we can see is that basically the light curve here of MAGIC is following a time decay, which is very similar to the one that we have in X-rays, in this case from Swift XRT. And so I mean, this tells us that most probably the emission that MAGIC detected belongs to the afterglow phase of the GRB, where we have this smooth decay in time of the emission. And so also this tells us that probably there is some link between the processes that are producing, in this case, the X-ray and the very energy emission. So for the X-ray, we know that it's due to synchrotron emission. And so, I mean, most probably at the time when we detected this GRB, we were thinking, okay, maybe it could be synchrotron, but it could be also some other process. And actually, we found out that most probably it's not synchrotron, the process that is producing the very energy emission detected by MAGIC, because the energy of the photons detected by MAGIC are above this maximum energy that for which gamma rays can be produced by synchrotron, this so-called Barnov limit, at least in this one zone model that we were using. And so basically we could fit and we could explain the emission by MAGIC not basically with a model considering the synchrotron emission for the low energy photons, in this case in the X-ray regions, but then the self-synchrotron Compton, so basically inverse Compton, to explain the MAGIC data. In this case, we had also some other effects to take into account to, for example, this Klein-Nichian regime that makes the spectrum softer at the very energies. And so with this, basically, we were claiming that we have a new component in the afterglow of the GRBs. So we have the synchrotron, but then at the very energies, we have the self-synchrotron Compton. And also we found out that by this modeling, the parameters that we were obtaining are basically very similar to the ones that were obtained in previous GRB studies in the afterglow. And so this could be a hint that this very energy emission might be common in GRBs. And then actually we had another one in December 2020, 2012-16C. So actually these we are basically finalizing the paper. We are basically finished with the modeling, so I hope that by the end of the year that the results on this GRB will be out. The interesting thing about this GRB is that it's a redshift 1.1, so it's very far away, but also this means that the absorption by the ABL is it's large, and so also the systematics connected to this should be evaluated carefully. Actually, I will also show you about this 160821B, which it's a short GRB. So while the others were long GRBs, this one is a short. And so short GRBs are thought to be connected also with gravitational wave emissions, because basically their progenitors could be these binary neutron star mergers, and actually this one had the kilonova emission confirmed. So at the time there were no interferometers operating, but due to this kilonova emission detected by this GRB, it could be very well that the progenitor was most probably a binary neutron star system. So while we have just a free sigma signal, we went on in any case with the modeling of this GRB. But what we find is that if we do some kind of the same modeling that we did for 190114C, so this synchrotron plus self-synchrotron Compton modeling, we see that this is basically in tension with basically what we get from MAGIC, assuming that the signal is real. And so this may be a hint that maybe in short GRBs, the emission processes are somehow different from the ones that we have in long GRBs. And actually also these give some exciting perspectives for the next observation run that will start hopefully in March 2023, if it is not delayed anymore. So yeah. And instead with the LST1, actually, of course, we follow up GRBs, but up to now we have no detection. But also I remember that we are still in commissioning phase, but it would be really nice to detect a GRB while still in commissioning phase. And also we have to take into account that the reaction to GRBs is not automatic yet in LST. So now there are still the operators that have to confirm the observation, but yeah, hopefully soon we will have this automatic repositioning and also the fast repositioning. So we have to do some commissioning of the fast movement in the elevation. And actually, yeah, next challenges for GRBs with the Cherenkov telescope, I guess that since now between MAGIC and S we have only 4 GRBs. Basically, we need yeah, to have more GRBs that at very energies in order to to know more about their emission at the very energies, not only in the afterglow, but it would be really nice to have a detection in the prompt, even if this is really difficult because of this delay of observation that we have with ACTs. And also, as I just mentioned with this last GRB, the connection with gravitational waves and short GRBs. And so hopefully in 04 we will have more bi-neutron star events that we can follow up with Cherry-Pur telescopes. And also you can do some new physics. So for example, for 1901 14C, we did the study of Lorentz invariance violation, where we put upper limits on this. Of course, in this case, they are not so constraining, but hopefully, for example, if one detects a far away GRB in the prompt, then these upper limits, then they can be really competitive with studies, for example, from flares of AGNs. Gravitational waves. Well, here I guess Halim already introduced the difficulties in this. So we have large localization, and also we have some delay introduced by the interferometers to get the localization that afterwards is provided. And also sometimes we have that these the GRBs that can result, for example, from bi-neutron star system, they are not on axis, but they are off axis, so they are not so bright, and so their emission can reach the peak at later times, and so they will not be so bright at the beginning. And basically here, as Alim showed, we need an observational strategy that tells us, okay, where to point, depending on the information that we get from the interferometers. And here, for example, I was showing one example of this bi-neutron star event that was sent during the last observation run. And so you see, for example, in the 50% confidence level area is around 800 degrees squared. That of course, for the ACTs, it's not possible to cover with just one pointing, but we need to do some kind of tiling. And actually, I think this was taken by the paper by Halim. So this is basically more or less the scheme that he showed. So all the information from interferometers is used in a scheduler in order to decide which pointings in the tiling will be observed with the telescope. And this is, for example, an application with LST1 for the two different events. Actually, here, this event on the left is from Fermi GBM, because you can apply this same tiling procedure to also Fermi GBM alerts, which have this large localization. And then on the right, instead, an application of this same algorithm to gravitational wave events. And so basically with this, at least for quite well localized events, you can cover the localization region with few pointings. And then, of course, as I said at the beginning, you have the real-time analysis that will tell you if in one of these pointings you have some significant signal. And then, of course, these will be used in order to recompute the schedule, in order to stay more time on that pointing, and also send a science alert to the outside community in order to focus on that particular point. And then, as mentioned before in the questions, basically, these kind of events are also interesting, maybe to follow up at late time. Actually, this is, again, this bi-neutron star system from 2017. So at the moment of the alert, at least from the MAGIC site, this was not visible. It was very low on the horizon. But we did a follow-up, basically, almost half a year later. It was, I think, February, March 2018. And we have some upper limits, but of course these are not sensitive enough to constrain possible TV emission. And then here on the right, basically we have different predictions of the gamma ray emission depending on the viewing angle with respect to the GRB. Just to tell that, if the viewing angle is not aligned with our line of sight, of course you will have that the emission will peak at later times, and of course it will be less bright. Finally, neutrinos. So somehow neutrinos are combining the challenges from gravitational waves and GRBs. So with respect to the localization, of course, we are not at the level of gravitational waves. We are way better. We are at the level of 1 degree or less. And basically, we have different streams, so all coming from IceCube at the moment. So we have these gold and bronze streams, which are high energy astrophysical neutrinos with different probabilities of being astrophysical. And then also we have private streams where basically they look at multiplets of neutrinos coming or from predefined positions given by some source catalogs, or just looking at all the sky without any assumption on the source. And so, basically both MAGIC and sometimes soon LST receive also this kind of private alerts. And basically, actually, we are working together with the other ACTs, so HES, Veritas, and FACT, in a paper that will resume, basically will summarize the observation that we did on these singlets and multiplets of neutrinos. So I hope that also this will be coming out soon. And I guess the most interesting event is that the one that was already shown this morning in the first session. So these Blazar TXS 0506, and I guess there is maybe what I can add in this is that basically at least from the MAGIC side, it could be that the follow-up would have been done earlier, because we did this follow-up only when we received this alert from Fermi saying that the blazar was flaring, and so only after that we observed the source. So probably we could observe it earlier, and maybe we could have seen something else much closer to the time of the alert. How much time do I have left? Because I'm just going, but at some point, I guess. Okay, nice. And of course, this was a super interesting event, even if this connection is at the level of 3 sigma. But then we know well from later studies that maybe blazar, they are not, they are only part of the picture for the neutrino emission of this diffuse flux. Also, the sources actually may be faint in gamma rays, and also other sources might contribute. So we were discussing this morning about, for example, tidal disruption events, or maybe novae, as we were also saying. And the last one that I will show is it's about novae. So here I'm showing the results about LST1. Actually, I'm not showing the one by MAGIC because I was thinking that maybe it was more interesting to show the one by LSTs, just to show that LST is entering the game in this transient business. So this RS of Yuki is a recurrent symbiotic nova. So there is a white dwarf with a red giant companion, and so basically there is a accreting material that is going on the white dwarf, and there can be some thermonuclear explosion that will power the nova. And here we have that the period of this nova is around 15 years. And so we had a flare seen by Fermi on basically last August of the last year, and then also in optical. And basically this was first detected by HES, but then also by MAGIC, and actually this is the first nova that has been detected at very high energies. And both results by MAGIC and HES suggest that this emission in gamma rays, very energy gamma rays, may be due to some hadronic model. And so also coming back to what was commented this morning, so since it is an hadronic model, we also may expect neutrinos, but actually, at least from the MAGIC paper, the energy of these neutrinos is less than the one that IceCube is detecting, and also, it should be more or less in the energy range of Super Kamiokande, but the fact that Super Kamiokande doesn't have a too large effective area makes the rate of events of detecting neutrinos quite low. And here, indeed, as I said, I'm showing the results by LST1. So also LST detected this nova, and actually the points by LST are quite compatible with the ones by MAGIC and HESS. So this is a sign that LST can do well transient science, at least as good as MAGIC and HESS, hopefully better, especially in the low energy regime. And so, yeah, also at least for LST, so HESS and MAGIC papers are out, but there will be one by LST soon. And with this, I come to my conclusion. So I talked about GRBs, gravitational waves, neutrinos, and novae, but actually there are many other transients that are followed up with MAGIC and LST. And of course, because of time reason, I couldn't speak about them. But yeah, some of them, for example, also in connection with neutrinos, so this multi-messenger picture are very interesting. So for example, reception events. So expect that there will be also some technical developments, and I hope that during this week maybe we can discuss about this in more detail. And also, yeah, I hope to have soon also some transient observation with MAGIC and LST1 due to this increased sensitivity. And as I said before, yeah, I look forward to interact with the other communities to work together and have some suggestions on how to improve our transient program. So that's it. Thanks.